This video looks at equations, substitution, and functions, with an eye looking at function evaluation using formulas as the input. So I want to start by thinking about an equation as any statement that says two expressions are equal. For example, A equals B. We can think of each side of a card as representing one side of an equation. So the equation A equals B, on one side the card would be A, and if we turn the card over, we see the value B. What this means is anytime I have an A, I can turn this card over and replace it with B. So for example, if I had an expression 2A minus 3, that can be rewritten by imagining that A is a card, and 2A minus 3, I turn the card over, and it becomes 2B minus 3. So we have an equation. Our new equation is 2A minus 3 is equal to 2B minus 3. And this was using the earlier equation A equals B. This gives us a new equation, which we could think of as its own card. 2A minus 3 on one side, and 2B minus 3 on the other side. So functions define a particularly powerful principle of substitution. We think of a function as defining a relationship between two variables. There's an input variable and an output variable. And so my input variable of x typically is used, and it gives me an output variable of y. So we're going to think here of y as an output, x as an input, and so when I see f of x, I need to think of the value inside the parentheses as my input. So if I had an equation that defines a function, there are actually two levels of substitution. An equation like f of x equals x squared minus 3x, well, that's a simple equation, so we could think of it as a card. On one side is f of x, and on the other side is x squared minus 3x. Every time I see f of x in a formula, I can replace it by the formula x squared minus 3x. So there's an expression substitution. But the way that function notation is so powerful is that the input represents a second level of substitution. If the input is changed to any expression, it could be a number, it could be a formula, the variable in the output, wherever the input variable appeared, so for us there were two of them, x appears in x squared and also in 3x, each of those is going to be replaced by my input. So for example, f of x equals x squared minus 3x. If I put as an input the value negative 2, the x's in the formula on the other side of the card are also replaced with negative 2. If I replace x with 2t, the formula on the back, the replacement, is the quantity 2t squared minus 3 times the quantity 2t. And we need to emphasize that the input expression, whatever appears between the parentheses after the function name, have to be considered as a single block. So when we write it out on paper, we're going to need to be sure that the input formula is put in parentheses. So for example, f of minus 2 would be equal to the quantity negative 2 squared minus 3 times the quantity negative 2. And f of 2t, well, that would be the quantity 2t squared minus 3 times the quantity of 2t. And this is important because it's not just the t that's squared, but 2 times t is squared. If I were to simplify that, that would be 4t squared minus 6t. So let's look at an example. Suppose I had a function, f of x equals x squared minus 3x, and I was asked, find f with an input of x plus 2 minus f of x. Well, how would I think through that? First, I would recognize that my function f is used twice, so I'm going to have two substitutions. And I've represented that here with these two blocks. I need to know what f of x plus 2 is, and I need to know what f of x is. To think about what f of x plus 2 is going to be, we're going to build what we need to replace the first card with, I think of x at the input as this second level of substitution. When I replace the input with x plus 2, both of my x's in the formula are replaced with or substituted with the quantity of x plus 2. And so I'll write this as an equation. My function f of x plus 2 will be equal to the quantity of x plus 2 squared minus 3 times the quantity of x plus 2. Now I want to simplify that, so I'll expand it. X plus 2 squared means multiply by itself. I distribute that all across, maybe using FOIL, so that x plus 2 squared is replaced by x squared plus 4x plus 4. And can you imagine thinking of that as a card being turned over? X plus 2 squared, the back side is x squared plus 4x plus 4. And then minus 3x plus 2, that negative 3 distributes across both x and 2, and so I get minus 3x minus 6. And then I simplify, and I get x squared plus x minus 2. Well, that gives me the formula that I'll use in my substitution. The card that I have with f of x plus 2, the back of it in simplified form is x squared plus x minus 2. So I can imagine making that swap. The f of x, well, that's defined at the top, and so f of x is replaced by its quantity, x squared minus 3x. Now how would I write that on paper? Well, I'd write an equation, f of x plus 2 minus f of x is equal to the quantity of x squared plus x minus 2, see that's where the f of x plus 2 was, minus x squared minus 3x as a quantity. That's where f of x came from. Well, I need to expand and simplify this, so I'll distribute the negative sign. So I get minus x squared plus 3x as the last two terms. My x squared minus x squared cancel, and x plus 3x simplifies to 4x. And so my formula, f of x plus 2 minus f of x, has simplified to 4x minus 2. So that's an example of how I use function evaluation to simplify formulas that involve the evaluation of a function involving a formula.